Okay, so we are now on week 4 of EEE 153. Hopefully nakaka-keep up pa kayong lahat. So for this week, uh, let's just look at the study guide. Narinig ko na lahat. Pwede ba kayong mag-yes or no dun sa Zoom? Yeah, thank you. So for study week 4, learning outcomes, understand C code to MIPS, and then convert integer arithmetic from C code to MIPS, convert arrays from C code to MIPS, and convert procedures and stacks from C code to MIPS. So sabi sa study guide, read the C code to MIPS files in week 4. So ito yun. Let's start with this one. Dito naman, no? So, translating C code to MIPS, why do we do it? So, C is relatively simple, close to the machine, and C can act as a pseudocode for our assembler program and gives us some insight into what compilers need to do. And then, yun, yung MIPS basically yung under the hood. So, do you need to know how the carburetor works when you drive your car? Hindi naman. Pero kung ikaw yung mechanic, kailangan mong malaman. So, okay. So, register conventions, I think na-cover naman to sa previous videos. Pero, reminder lang. Parang, ayan lang siya ulit. So, si 0, always 0. Si number 1, used by assemblers. Si V0 to V1s, usually for return values for subroutines. A0 yung arguments, temporaries, yung mga sinisave, more temporaries. Tapos this is yung kernel trap handler, so hindi mo ginagamit. Global pointer, stack pointer, frame pointer, and then yung return address for subroutines. So yung hidden registers natin is yung tinatawag na program counter, which stores the address of the current instruction being executed. And then yung IR or instruction register, which stores the actual instruction being executed. So arithmetic expressions. So for example, let's say we have 5 integers, f, g, h, i, j. If sa C gusto natin f equals g plus h minus I plus j, ang sinasabi lang nun, pag ginawa natin sa assembly, kailangan natin ng multiple lines. So kahit isang line lang siya sa C, multiple lines siya sa assembly. So first is kailangan muna natin si G plus H, and then kailangan natin si I plus J. So, nag-assign muna tayo. Si S0, siya yung mag-store kay G plus H, which is S1 and S2. And then si S1, S3 plus S4, which is in IJ. And then subtract natin sila, yung G plus H, tsaka I plus J, which is S0 and S1. And nagawa na natin siya. Actually, may video patungkol dito later. Medyo ulit-ulit. Next is, what if gusto kong gumawa ng conditional if sa assembly? So, kumare, if I equals j, I plus plus. And then, after nun, j minus minus. So, basically, mag plus 1 kay I, if equal sila. Otherwise, even after nun, magma-minus kay j. So, even if naging true to or naging false siya, magma-minus 1 pa rin tayo sa j either way. So, actually, ito yung ibig sabihin nun. If condition is true, we fall true to execute the statement. If false, jump to next. So in assembly, we need to jump if the condition is true. And then we need, so in assembly kasi, we jump if the condition is true. Pero for our C statement, gusto kasi natin, nagja-jump siya sa J pag false. So kailangan natin i-negate yung condition. So ang ginagawa dito is branch not equal S1, S2. So ibig sabihin, magba-branch tayo if hindi equal si S1 or S2. Kasi if equal sila, we want to do yung next operation, which is I++. Otherwise, gusto natin mag-jump na lang dun sa next instruction, which is J minus minus. So, nasusundan pa ba? Next is pag if else. Okay, itong muna sa taas yung tingnan natin. So, using yung previous logic, instead na equal yung i-check natin, we check if hindi equal. And if hindi equal, punta doon sa else. Although may problem dito. If hindi tayo nag-branch, gagawin natin to. And then yung next instruction is ito, which is gagawin pa rin natin. Although in the initial case, since nasa else siya, ayaw natin gawin yung nasa else statement pagka naging true yung nasa if statement. So instead of doing this, kailangan natin maglagay ng additional jump na instruction dun sa end ng if statement natin. So now, if hindi tayo nag-branch, which is ibig sabihin equal si I and J, we do the addition operation, and then after we jump to the next. So skinip natin yung nandito sa else. So hopefully ma-highlight yung difference na yun when we are transitioning from C to assembly. Then, if may multiple tayong conditions, medyo complex yung magiging dating actually. So, let's say condition 1 is I equals J, and then condition 2 is I equals K. So, short circuiting occurs when condition 1 evaluates to false. The control flow then jumps over to condition 2 and the if body. So, if condition 1 evaluates to true, we want to check condition 2. If condition 2 evaluates to false, we jump again, this time over the if body and then to the else body. So if condition 2 is true, we fall through to the if body. So basically, ito lang naman yung tsura nun. Kailangan lang natin mag-check twice. So in C, it looks like a simple statement na isa lang. And then pagdating natin sa assembly, we need to check yung condition 1. If true siya, we continue. I mean, if yung gusto natin condition I equals J, so if hindi sila equal, we jump. So pag equal sila, we continue. And then we check the next condition. We check the next condition. Then go to add I. And then since else, may else statement tayo dito, we need to jump to the next. And para hindi na natin i-execute yung nasa else body. So actually, yung sa else, pwede yung patundagdagan. And as long as yung label natin is dito sa add, yung jump na to will jump over yung next instructions na yun. Then, if naman or, yung condition natin, yung sa end, kailangan natin daanan both. So, pag sa or, basta may isa na mag-true, magja-jump na tayo. So, or, ayun, may jump na rin. Pwede na siyang, yung first check natin is if it is actually true. And then if it's actually true, magja-jump na tayo doon sa if. And then yung next check, in next branch operation natin, siya yung mag-check if doon sa reverse nung condition 2, which is if not equal. Para if equal man siya, we continue dun sa if. And then if false siya, we go to the else. Okay. When we, pag dito naman sa switch, so familiar pa naman lahat sa switch ng C++, di ba? So if yung switch I, so depende sa value ni I, yung pupuntahan nating case. So if I equals 1, ito yung gagawin. If I equals 2, ito yung gagawin. If I equals 3, ito yung gagawin. So actually dito ma-highlight kung bakit may break yung mga switch statements. So for example, ayun, yung case 1, we set our temp to 1, so si S4. And then i-check natin si S1, which is yung I, and compare it to S4. So if false, we branch to case 2. Or if hindi sila equal, we go to case 2. If not, punta tayo sa C1 body, which is nandito sa baba. And then for case 2, papalitan natin si S4, gagawin natin equal to 2. And then we check again, not equal ba sila? If not equal sila, we go to case 3 condition. If equal sila, we jump to the C2 body. So basically yung nakikita natin dito is, nandito lahat sa umpisa yung mga conditional statements or yung pag-check. And then yung body natin is nandito sa baba. Then, di ba yun nga, si case 1, I++ lang siya, wala siyang break. So if si I equals 1, gagawin natin si I++ and gagawin natin si I plus equals 2 kasi wala tayong break statement. So here, yung break statement actually translates to a jump na command. So as you can see here, if we jump to C1 body, gagawin natin instruction na to, and then gagawin natin instruction na to, and then we jump to exit. So kung whatever pa yung susunod dyan. Then next is if kaya natin mag-conditional statements, kaya din natin mag-loops. So ang difference nun sa, so yung while statement natin, pwede natin siyang gawing parang if statement. So if yung condition natin is true, gagawin natin yung nasa while, and then we jump back to yung pag-check ng if condition. So while the condition is true, we go back to the if statement. So basically, yun yung nagpapa-loop sa kanya. So here, S1, S2, we branch if greater than or equal to si S1 kay S2. So basically, yun yung reverse ng condition natin sa while loop. So parang sa if statement kanina, ni-reverse natin siya kasi if true siya, yun yung nag-a-allow sa ating mag-jump. And if false siya, magko-continue lang siya sa next statement. So here, if S1 is less than S2, this statement will be false, so we don't branch. So we go to add I, so K++, and then we add, which is I equals I times 2. So ginagaya lang natin to. And then we jump back to yung label na L1. So since nag-jump back tayo ulit sa L1, i-check natin ulit yung condition. And if false yung condition na to, which means true yung condition ng loop, magtutuloy pa rin tayo dito sa baba. And then ulit-ulit lang yon. And then if this ever becomes true, or when I is already greater than J, pupunta na tayo sa done. So next is yung for loop. Basically, parang while loop lang siya na may, well, for in C, it makes it convenient. Sama-sama yung ating tatlong requirements for a loop, which is yung initial condition, yung condition to check, tsaka yung update statement. So since assembly, yun nga medyo mano-mano ang lahat, basically yung initialization, mapupunta lang siya sa before ng while loop. And then yung condition nandito, and yung update is nasa dulo ng while loop. So from for, pwede natin translate to while. And then yung while, kaya natin translate to if. And then ganun lang din siya. So hopefully, well, pwede naman kayo mag-raise ng hand if may question na kayo now. So hindi naman kailangan matapos ng video bago kayo mag-tanong. Next is arrays. So given an array of integers, calculate the sum of all elements. and then all the positive elements, all the negative elements. So here yung C program natin. So meron muna tayong initialization of variables. So int I, which is just a counter. Size, yung size ng array natin dito sa baba. Sum, siya yung sum ng all ng elements. Pos yung sum ng positive elements. Neg yung sum ng negative elements. So ito lang yung array. And then we initialize yung sum variables natin. So si sum0, si pos0, si neg0. And yung for loop natin, initialization, I starts at 0 as long as I is less than size, and then I++ after each iteration. So first is check yung sum. I-add natin si array element sa sum. And then if array element is positive, i-add natin siya kay pos. And if negative siya, i-add natin siya kay neg. So anong magiging itsura niya sa ating code? So here, initialize lang natin yung registers. So let's say yung size is nandito. And then, ayun, ilalagay lang natin siya dyan. And then ito is just initialization na 0, 0, 0, si S2, S3, S4. So after nito, S1 will contain yung value ng size. Then ito, si I, which is i-assign natin kay S5, it starts at 0. And then S6 will be storing yung address ng ating array or yung first address ng first element ng array natin. So, ayun. So meron tayong label 1 dito, which is signal, which means yung start ng loop. So since ang ating condition sa loop is I less than size, yung branch instruction natin is greater than or equal to ba si S5 kay S1. So si S5 ulit, siya si I. Si S1, siya si size. So if I is greater than or equal to size, we go to done. So otherwise, we load kung ano man yung pinopoint ni S6. So yung current na content ng array. And then we add it to sum. And then here we want to check if it's positive. So pag chinek natin yan, we branch if less than or equal to 0. So BLEZ, less than equal to 0. So if S7 is less than or equal to 0, that means negative siya. So we jump to neg. And then otherwise, i-add natin siya dun sa sum natin na pos. So after nung line na yon, we jump kasi we know na pag positive siya, hindi ka negative. So punta ka na dun sa update statement. Then susunod is yung sa neg. We still need to check kasi if negative ka, hindi ka naman, if less than 0 ka, hindi ka naman automatic na negative kasi pwede ka pang maging 0. So actually, ang mag-check mo lang dito if equal to 0, punta ka na sa update. Pero otherwise, actually, hindi siya ganun ka. Actually, hindi rin nagmamatter kasi kung 0 ka naman pag in-add mo, walang effect. So medyo unnecessary na command. Pero I mean, just to be sure, we need to check kasi gusto natin kopyang-kopya natin yung nandito. We check if positive, we check if negative. So, ayan. So, mayroong ganung branch equation, branch command. And then, yun nga, if negative, we add it. And then yung update statements natin, I++. And then si S6, remember, siya yung nagsustore ng address natin. So, excuse me. For the next iteration of the array, mag-add muna tayo ng 4 para mag-point na siya dun sa next element ng array. Then, and balik tayo sa task ng loop. Then, after nun, you should be done. So, ayun, so dito lang nakadefine yung size na ito yung laman, and then si array na ito yung laman. Okay, yun na yung first. Ano, may isa pa. So yung next na file, so actually ito ata is basically yun din. You need to be familiar with yung concept ng assembly language, yung paggamit ng registers, instruction formats. I think this is from a book or lecture series siguro. Then, ayun. Actually, medyo in-explain lang in detail yung mga ginawa natin kanina. So, if we have a condition, tapos may block, and then else, tapos yung block for else. So, ayun lang. If we want to convert it to assembly, yung conditional natin, siya yung unang instruction. Then, ayun, pwede mo lagay dito yung else, or yung ginagawa natin kanina is, yung conditional is ninegate natin. So, yung if block or yung then block is dito natin nilalagay. And then, yung else block is dito naman sa baba natin ilalagay. So, medyo baliktad yung notation. So, you can also do that. Pero, yun nga, mas madami kang labels dito. Pero, so, nasa kung ano na lang yung prefer yung gawin. Then, okay. So, ito lang yung summary. Kung ano yung condition, ano yung equivalent niya na instruction. So, if A equals B, branch if equal, branch not equal, branch less than, branch greater than, branch less than or equal, branch greater than or equal, and then branch equal to 0. And then actually, meron pa yatang branch not equal to 0. So, B and EQ yata yun. Then, next is yung loops. So, actually, kung papansin nyo, mas madali gumawa ng do-while sa assembly compared sa C. Yeah. You'll notice why merong do-while kahit konting difference lang. So, yeah, I think we covered this sa kanina. And then, yeah, ito lang din yun. Initialize T0, initialize T1. And then yung loop natin, we branch if equal. So if equals to T1 at T0, we go to the end. Otherwise, we add and then jump dun sa loop na label. So yeah, no self-respecting compiler will ever produce the loop in figure 3.2. Pero ito yung, since meron tayong isang extra instruction dito na hindi actually natin kailangan. Pero, ayan, just to make, para lang makita nyo na mas parang 1-for-1 yung translation. So, sample program. So, this one is, kinukuha natin yung length ng isang string. So, basically, chine-check natin yung contents ng string. As long as hindi sila equal kay null, ayun si tawag dito? Yung end of string na character, \0. Okay. May nagtatanong pala. Ano yung meaning ng LA? Wait, saan kasi nakita yun? Dito ba yun? Basically, since, okay. Pag L yung start, kasi usually ibig sabihin niya load. And I think pag A, you can usually guess kasi, pag kumari sinabing I, that means immediate. So, immediate number, which is 10. Then I'm assuming pag A, address siguro siya. Since kanina we were dealing with arrays, so most probably load address yung instruction na yun. Although you can always double check naman sa reference manual. Ay, nagbigay ba si sir ng reference manual ng MIPS? Like yung complete instruction set. So, if ever wala, I think pwede naman ako mag-upload nun. So, going back is, dito naman merong LDU. So, load, ano kaya? So basically, ibig sabihin niya is load the next character into T1. So I think since byte, so baka load byte upper, so upper byte siguro. Although I need to double check. So basically, pero what you need to know is that for this command, you are loading the next character in our string dun kay T1. And then, yeah. So ito yung function natin str din. So initialize yung counter to 0. Yung start ng loop natin is here. So yung start ng loop, yung una niyang gagawin is i-load yung character kay T1. And then if T1 is equal to 0 or yung \0 na character, we go to exit or we exit. Otherwise, we add I. We add dun sa string pointer and we add dun sa count. So kanina yung ina-add natin sa string pointer natin was 4 because we were dealing with integers which are 4 bytes long. So in this case, since characters lang, +1 lang tayo, kaya yung next character natin sa string would be just +1 and +1 yung sa address. So you'll notice here yung branch natin is hindi siya nasa taas ng loop. So you can do that as well. Although yun nga, ang more common practice is yung branch operation natin is actually nasa start ng loop kasi yun yung mas intuitive if galing ka sa C programming. Pero yun, it's really a matter of preference. Walang mas tama, walang mas mali. Although minsan actually baka maging mas efficient if ganito yung gawin mo. Kasi I think ito yung sinasabi niyang merong extra instructions kasi dito na kahit hindi na gawin. Ayun, actually ang probably mangyayari dito is yung jump operation na to, pwede siyang palitan ng branch na operation. And mag-occur yung branch operation after natin mag-add I. So after adding I, we branch tayo if less than dun sa loop, pupunta sa taas. And then, ayun. So parang one instruction less siya. Although, kung hindi naman kayo nagtitipid sa instructions, if mas comfortable kayo na mas mukha siyang C, I'd recommend na yung branch operation nyo is after no label. So yan. This is a remarkably simple procedure. It gives a good demonstration of the loop construct in action, etc., etc. So pwede nyo naman basahin in your own time, I think. Ayun pala, nakalagay pala dito. LVU, load single unsigned byte. Okay. So as you can see, technically hindi requirement kabisaduhin lahat ng instructions. Although yung pinaka-common na ginagamit, supposedly dapat alam nyo. Kaya yun yung mga tinatanong naman usually. So next is another program that finds and returns the maximum value in a unsorted array. So in C, basically mag-start muna tayo, i-load natin, we assume na yung maximum is nasa array 0. So i-assign natin siya dun sa temporary variable na maximum. And then we go through the loop, check natin each element dun sa loop. Excuse me. And then if ever merong element na mas malaki kay maximum, siya na yung bagong maximum. And then we just go through the loop. So basically another example na, pero in this case, ito while loop lang siya sa loob. And then in this case is merong if statement sa loob na for loop. So we should expect more labels and jumping. So here ang ginawa niya is load word kay T0 yung first array value. So Si T0, we'd expect siya yung nagko-correspond kay maximum. And then si T1 starts at 1. So si T1 natin is I. And then yung, actually hindi ko lang saan nakastore yung size. Pero I think andyan na yan. So, ayan. So actually nasa A1. Since di ba meron tayong dalawang arguments dun sa ating function, we assume that array is stored at A0. And then si size is stored in A1. Then we check if T1 is equal to A1 or when I is equal to size. So actually, yung check na dito is I equal to size instead of I less than equal, or I less than size, since we want to exit pag equal na sa T1 at saka si A1. So pwede ko ba itong gawing branch greater than or equal to 0? Greater than or equal to? Well, yes, pwede naman. Pero since given yung nature ng program, hindi naman siya magiging greater than. Hindi naman magiging greater than si T1 kay A1. So probably okay lang na BEQ lang yung gamitin. So after checking if umabot na tayo sa dulo ng array, we increment the pointer natin, si A0, by 1 word. So since this time integer yung mga ginagamit natin, so plus 4 yung ina-add natin sa address. And then si loop counter plus 1. And then we store yung next array value na yon kay T2. So notice na nag-start tayo at 0 offset kay A0. So by this time, since nag-increment tayo ng 4 kay A0, yung pag-load word natin dito is makukuha na natin yung next element. And then yung next is we branch if less than or equal si T2 kay T0. So that means na if less than or equal to si T2 kay T0, which is yung maximum, we go to the end of the if statement. Otherwise, punta tayo, i-move natin si T2 kay T0, which means if you're not less than or equal to, you're greater than. So T2 is greater than T0, we move the value of T2 to T0. Then yung end if natin is just jump back doon sa loop. So may argument dito, meron kayong pwedeng argument dito, if less than or equal to na si T0, ay si T2 kay T0, pwede na actually tayo mag-jump. Pwede natin lagay dito yung loop. Although this assumes kasi if ever gusto mong dagdagan yung for loop mo, dito mo idadagdag sa end if. Pero in this case, since jump lang naman yung instruction, pwede ko tong gawing naka-jump na agad sa loop. Although hindi natin pwedeng tanggalin yung command na to, kasi if naging equal man siya, if ginawa natin yung command na to, ginawa natin si move, we still need yung jump operation. So, ayan, preference na lang, parang extra label lang siya. So, medyo preference na. And then this program illustrates both the if and the loop constructs. You should be able to notice how difficult it is to keep track of yung variables. Actually, oo. So, it would be helpful if meron kang small table, yung may table ka nung registers mo and yung variables mo on a piece of paper, or kung nasa desktop kayo, pwede nyo lagay sa notepad usually. And yun, baka malito kayo kung aling register ang ginagamit nyo for which. And then it's also very instructive to attempt to write this program in a slightly different way. So make the loop count down, or if you have to look for the minimum value. So, ayun. So, malay nyo, lumitaw sa quiz. Pero, actually, yung quiz nyo for this will be manggagaling pa rin kay Sir Rosales. Okay. So, balik tayo sa study guide. Yay! Okay na tayo sa activity 1. Woo! So, okay. We just need to watch the videos. So, after nito is 48 minutes na lang, and then we're probably done. Okay. Tingnan natin kung magaling yung internet ko. Kaya ba natin 720p hanggang dulo? Let's go convert. Yes, so kita naman sa screen. Yes, yes. So, para naman baka kasi magkulang sa bandwidth, tago ko na yung video ko. And let's go.
Welcome. This is the first part of a multi-part series about programming in MIPS assembly. This first part is about integer arithmetic. The assembly language program will be using the MIPS instruction set. MIPS is a reduced instruction set computer, or RISC, primarily used in the embedded systems application domain. MIPS was a response to the growing complexity and increasing cost of what are now known as CISC, or complex instruction set. The guiding principles of MIPS include simplicity favors regularity, smaller is faster, make the common case fast, and good design demands good compromise. This is known as an instruction set, and the resulting processor based on MIPS is an instruction set architecture. Computers may have different kinds of instruction sets. For example, your typical Intel processor has an Intel x86 64-bit instruction set. The available instructions of the computer tell the processor what to do. Instructions are composed of an operation, specified by an opcode, and a number of operands, which the operation uses. Classes of operations include arithmetic, logic, branch instructions, jump instructions, and load store instructions, and a few others. Operands typically include registers and hard-coded constant value numbers, or immediates. Registers are the local storage within a processor. Word size is the number of bits in an instruction, and often the general purpose registers are matched with the word size of the instruction set. A processor includes a register file, which is a set of general purpose registers that programs use to manipulate data. In MIPS 32, the 32-bit architecture of MIPS, there are 32 general purpose registers numbered $0 through $31. These registers are indexed by the numbers 0 through 31 within the instruction. $0 is a special register that's hardwired to always give the value of 0. Other registers have mnemonic values associated with them that are used to help when writing assembly level programs in order to adhere to the correct behavior expected by programs that have to interact with each other. These mnemonics will be important later, but aren't too important right now. So let us begin with addition. In a high-level language such as C, we write addition like this: A equals B plus C. In assembly language, addition looks something like add A, B, C. Or for a subtraction operation, such as D equals E minus F, we'll say sub D, E, F. Now, different assembly languages will have different orders of operands. In MIPS, the destination operand usually occurs first in the list of operands. So the destination operand here of A and D appear first before the argument operands of operands is important. Now, we can't actually use these variables A, B, C, D, E, F directly. Instead, we need to use register values. So, for example, we might consider allocating registers to, allocating variables to registers. So the A variable might be allocated to the $1, B to $2, C to $3. One of the jobs of the compiler is to allocate variables to registers when generating the machine instructions from a high-level language. So here we see an example of an expression written in a high-level language that's rather complicated. Let's assume that the registers have been allocated for the variables f, g, h, I, and j as $2, $4, $5. In high-level language, the expression f equals g plus h minus I plus j will get translated to MIPS assembly as follows. So we can rewrite the complicated expression in terms of the registers that are allocated to the variables. And we'll have to honor the order of operations when we generate the assembly. So the order of operations tells us to do the expressions that are first within the parentheses and then to do the subtraction. So the first operation is to add g plus h. The two registers for g and h are $4 and $5. So the MIPS assembly will do add $8, which will be the destination of the add operation, $4, $5. 4 and 5 are the source operands of the variables for g and h. $8 is a register that hasn't been allocated to any variables. It is a temporary storage location for the intermediate result generated for addition of g and h. The next sub-expression to calculate is I plus j. This is $6 plus $7, so the MIPS assembly instruction is add $9, $6, $7. Here again, $9 is a temporary register that's allocated to store the intermediate result of I plus j. Now that we have the two expressions, sub-expressions g plus h and I plus j calculated, we can do the subtraction. Subtraction is sub $2, that'll be the result, $8, $9. So that $8 minus $9 will get stored into $2. In the end, $2 associated with the variable f will contain the result of the expression as expected. We can also look at how this would be with the register mnemonics associated with those variables instead of the numbers. Here the variables allocated are $V0, which is used for return values from functions, $A0, $A1, $A2, and $A3, which are arguments for procedures or arguments for functions. And those temporary registers that we allocated are in fact $T0 and $T1, which do stand for temporary. We can also do arithmetic with constant values known as immediate operands, so the encoding of a number directly into an instruction. Here are two examples that are adding the value of 8 or subtracting the value of 4. Both add I for add immediate. Note that add immediate of a negative number is the subtraction of an immediate. Since we can encode the subtraction of an immediate using a negative operand for the immediate value, we don't need to have a sub-I instruction. Add-I operations can be used to add and subtract constant numbers as shown here. They can also be used to initialize registers to constant values, or they can be used to copy register values. Let's see some examples of these three uses of add-I. So assuming that the variables j and k are allocated to the registers $0 and $T1, in high-level language we may have these three expressions. J equals 0, initializing the value of j to 0. K equals j plus 10, just an addition of a constant number to a variable and stored in another. And then j equals k, which is the copying of a variable or copying from one register to another. So the first expression of initialization is done with an add-I of the destination variable, destination register, $T0, with the $0 register and then the constant number we want to initialize. Here we want to initialize T0 to 0, so we'll add I $0 with 0, which gives us a result of 0. Again, for just a normal addition of an immediate or constant number, we'll have an add I $T1, the destination, with $T0 and 10, so that T0 plus 10 will get stored in T1. Last, moving from one register to another is accomplished using the add I instruction to add 0 to the register that we want to copy. So here we're copying from T1 into T0, and we have add I $T0, that's the destination register, $T1, that's the source register, and the constant number 0. This will result in the value of T1 being copied into T0. Some other arithmetic operations besides addition and subtraction are listed here. Assuming that we've allocated the variables x, y, and z to the registers $S0, $S1, and $S2, the C expressions are equal to the MIPS expressions on the right-hand side. So z equals x minus y, which we've seen already, is sub $S2, the destination, S2 associated with variable z, $S0 and $S1. Multiplication and division follow. Z equals x times y is actually composed of two instructions. First, the mult instruction, $S0 and $S1, multiplies the two source operands. The result of the multiplication is actually stored in two registers, which we'll talk about next. They're stored in the low and high registers. The MFLO instruction is move from low. It will move the output of the low register into the operand S2 there. So that we'll get the low order result of the multiplication into S2. For now, we don't need to understand much more than that gives us the result of the multiplication, assuming that that result fit into a single register. For division, the same occurs, div of $S0 by $S1, and the quotient goes into the low register. So M from low, MF low, into $S2 will move the quotient into S2. The remainder is in the high register. There's also the shift operations. In C and C++, shift operations are represented by two arrows to the left or two arrows to the right, for shift left and shift right, respectively. So y equals x shifted left by a constant number n would be written in MIPS by SLL, which stands for shift left logical. The result goes into the $S1 register. X being $S0, the number would be put in place of the n. These special purpose registers are, for example, set as a side effect of instructions such as mult and div. To move the high and low registers to a general purpose register, there are special instructions MFLO, move from low, and MFHI, move from high. We saw examples of the MFLO on the previous slide. The arithmetic operations we've discussed so far assume that the numbers we're dealing with are signed. That means they are positive or negative numbers. They have a sign in front of them. We can also have operations that assume that their operands are unsigned, then meaning that the operands are assumed to just be positive. Unsigned operations have the instruction opcode ending with the letter U for unsigned. So add U, add IU, sub U, mult U, and div U are the unsigned variations of the instructions add, I, sub, mult, and div. In a C program, the unsigned modifier is used on a variable to declare that variable as having no sign, that is being positive. So an integer type can be declared with unsigned int x equals 0, for example. The equivalent expression in MIPS would be add IU, $S0, $000, using the add IU to initialize the S0 register to 0. Similarly, unsigned int y equals 1 is equivalent to add IU, $S1, $0 with 1, initializing $S1 to the value 1. Finally, the addition of two unsigned numbers is accomplished using the add U instruction. Here, add U, $S2, $S0, $S1 results in the addition of x and y into z allocated to $S2. That's everything for today. Thank you for paying attention, and I hope it's been illuminating.
Okay, so that's the end of the first video. May questions ba bago tayo mag-move on doon sa next video? Raise your hand, chat. So, going once, twice. Okay, so yung next video will be 20 minutes. If meron kayong chips dyan, kuha lang kayo.
Welcome to the second installment of the C2 Assembly Introduction to MIPS. Main memory is one of the three components of
a computer, and it's the component that stores the code and data for a program, which the processor fetches and loads and stores in order to get data in and out of registers and to move instructions into the processor for execution. Memory is byte addressed, meaning that the indexes in memory are all numbers of bytes, each byte containing, of course, 8 bits of data or instruction. In MIPS, memory is word aligned and big endian. A word is the size of an instruction in the processor. This is usually 4 or 8 bytes, depending on the processor type. 32-bit architecture, for example, uses 4-byte words, while a 64-bit processor uses 8-byte words. Typically, the size of the word is matched to the size of the general-purpose registers. Word alignment means that every memory address starts at a multiple of the word size. So in MIPS 32, every memory access has to start at a multiple of 4. Big endian means that when you look at the order of the bytes in the word, the most significant byte starts at the smallest address in memory. The most significant byte being the bits that contribute to the larger portion of the value of the word. Alternatives to big endian include little endian and bi-endian. As an example, let's consider storing the 32-bit hexadecimal value, shown here 4A3B2C1D, into the memory at an address starting at hexadecimal 1000. In a big endian architecture, the first byte of the word will be stored at the smaller address being the starting address. So here, the first byte is stored at the memory address starting the word, 0x1000. The first byte of the word is 4A. In hexadecimal, 2 characters of the hexadecimal value is a byte, because each character of hexadecimal is 4 bits, also called a nibble, half of a byte. So here, the hexadecimal values are stored as you look at the memory from smaller to larger in the order they appear in the word. So we have 4A at address 1000, 3B at address 1001, and so forth. In a little endian architecture, so here 1D is stored at 1000, and then the next least significant byte, 2C, is stored at 1001, then 3B at 1002, and 4A at 1000. Let's consider now how arrays are laid out in memory. Arrays are put in memory in the order in which the array elements appear. Here's an integer array getting 5 elements declared in C and initialized to these values, 313. The address of A0 is the starting address of the array. This notation ampersand means address of in C language. The address of the 0th index of the array is the start of the array. So the 0th value, 313, appears in the word starting at the address of the 0th index of the array. The next word of the array starts at the address of the 0th index plus 4. The plus 4 is because in the C language, in a 32-bit architecture, in the C language, the int type is a word-sized element, which means it's 4 bytes. Now, let's suppose that the start of the array A is in hexadecimal 1001000. That means that the address of the 0th element of the array will be that number, 1001000. Thus, we can replace our notation here with that number. And the 0th element starts at 10010000. The next element starts at that number plus 4. You can see that each subsequent word starts at 4 bytes offset from the previous, 048C, 0. Depending on the Endianness of the architecture, those 4 bytes may appear in different order within the word starting at the address. So let's consider array index 0, starting at the address 1001, 0000. When we load and store the value there, we get 313. When we inspect the contents of the memory in hexadecimal, in Big Endian, it's 0000139, where 139 in hexadecimal is equivalent to 313 in decimal. In a Little Endian architecture, these last two nibbles, the last byte of the word in Big Endian, is swapped in the memory. So that byte containing the hexadecimal 39 would actually appear first at this address. Array index 1, starting at address 1001, 0004. And the decimal contents of 78, when you load and store it, would have a Big Endian representation of 00000004E. And a Little Endian representation, 4E, 000000. Index 2 is similar. Now we look at the hexadecimal of this relatively larger decimal number. These pairs of nibbles appears in the reverse order in the Little Endian. So that the 02 again comes down to here on the most significant part of the Little Endian representation. Then 20 appears over here, and 0F over here. Finally, the 00s on the end swap. So you can see how the Big Endian and Little Endian are sort of mirrors of each other, but not exactly. And the last two elements in the array, the third and fourth indexes, are like so. There's not much new or interesting here to see. The memory instructions in MIPS are load word and store word. So load word to a register at the offset from the source register. This loads or reads a word of data into the destination register from memory at the memory address calculated by adding the offset, which is an immediate value, to the source register. The store word instruction will copy the word from the source register out to memory at the memory address located at the offset plus the value read from the destination register. This type of a memory addressing scheme is sometimes called base plus offset, where the base is the register and the offset is the immediate value that gets added to the register. To specify a constant address value, you can use a base register of $0 in MIPS. Base plus offset is relatively efficient for the common programming practice of incrementing through an array. Here's an example of load word and store word instructions. Consider that the registers have been allocated so that the variables here declared as G, H, and stored in $S1, $S2, and the base address of A0 is in $3. Then, to calculate G equals H plus A3, we would first do load word into a temporary register, the value located at offset 12, which corresponds with array index 3. This is an integer array, and so the array index of 3 is 12 bytes from the start of the array. 3 times 4 bytes per word. So we add 12 bytes to the base register address of $S3 that stores the base address of the array A. So now $t0 is equal to the value of array A, and we can add that value, array A3, to the register value of H in S2 and store it into S1. The next high-level language instruction is A4 equals H. Here, we reread A3 and re-add it to H. These two instructions are actually redundant. In another future video, I'll discuss about removing these redundant instructions in order to save execution time. So the assignment of H plus A3 into A4 is accomplished by doing a store word of the calculated value of H plus A3 out to the index of 16 offset from the base address S3. Again, 16 is equal to 4 times 4 plus 16 bytes from the start of A is the location of A4. Here's another example. This time, we're not going to assume anything about the register allocation yet. So a 5-element array A again, and we're going to calculate the summation of A0 plus A1 plus A2 plus A3 and store the result into A4. So the first thing to do is to get the address of A. In MIPS, the LA instruction is provided by the assembler. It is a pseudo instruction, and you may use it. It stands for load address. It gets the address of the label A associated with a variable into a register S3. So now S3 will equal the address of A. Now that we've got the address of A, the base address of A, we can now access elements of the array A by offsetting from that base address. So the first thing to do is to get the value of A0. We get the value of A0 by adding 0 to the base address of A. 0 to the base address of A. The base address of A plus 0 is the element A0 of the array. The next load word instruction does a similar thing, but this time it's accessing the 4-byte offset from the base of A, which is the 1th element of A, because each element is 4 bytes, because an int type is 4 bytes long. Finally, add $t0, $t0, $t1, adds the previously loaded values of A0 and A1 into the register T0. Load the value of A2 from memory, put it into the T1 register, and then add T1 into the previously computed value that we have in T0. So we're updating T0 by adding A2 to it. That gives us in T0 now the summation of A0, A1, and A2. And we need the value of A3. We get that by loading the right-hand side of the expression here. Now that we've got the right-hand side of the expression, we can store it into A4 using the store word instruction. We store the calculated value in T0 into the 4th word. Now let's talk about C structs. Struct is a concept in the C programming language for creating complex structures. Here we have a very simple structure which contains 2 integer types.
So, pause ko lang here since most of you, I think, galing sa C++ na background. So, lalo na sa 1-to-1, ang ginamit kasi natin nun is classes instead of structs. So, ang structs is siya yung parang classes ng C without the plus plus. Ang difference nila is ang struct kasi usually parang member mga parang attributes lang yung meron siya. So, wala tayong masyadong ay halos objects lang yun naman niya. Wala tayong masyadong methods. So if you remember yung sa classes natin dati, usually madami pa tayong methods dyan, di ba? Yung mga getters and setters. So for C, struct lang yung gamit and then directly ay na-access natin yung mga members niya sa loob. So wala nang getter and setter functions. So basically, a struct is a simpler form ng classes. So hopefully, hindi kayo masyado malito.
That would be a fraction type to store a numerator and a denominator. We can declare a variable of the type struct fraction by saying struct fraction f. Somewhere in memory, storage for this f variable is allocated. The address of f, ampersand f, part of f is the numerator value because it appears first in the struct declaration. The word of f plus 4, contains the denominator. Again, this is because the integer types are 4 bytes. So they perfectly fit into the word-aligned memory addresses. Structures in memory appear or are laid out in the order in which they are declared. The numerator field and the denominator field will appear in this order, numerator and then denominator in memory. Now when we declare this variable, we don't know where in memory it will sit, but we do know that when we access the f variable, we can access the numerator, and accessing f plus 4, the address of f plus 4, can access the denominator. Now we don't know what the values of the numerator and denominator are when we declare a structure. You cannot assume by default that C initializes variables to anything. So when you declare a variable, it's uninitialized, and you don't know what the value is. You can assign a value to a structure by using this dot notation, f dot denominator, which says the denominator field of f should be set to 20. Similarly, we can initialize the numerator, for example, to 10. In the MIPS assembly, this will be equivalent to having these instructions. Load address to T0 of f. So T0 is the basis address of f. Initialize a register T1 to be 20. And then store the value of 20, thus initializing the denominator field of f to be 20. Similarly, to initialize the numerator field to 10, we put a 10 into a register, and then we store the register containing the value 10 into the offset 0 from the address of f. Here we have the 5-element array from before and an instance of the struct fraction f before. The compiler could lay out the array before or after the struct. Here we show the array coming before the struct. The array starts at address 0x10010000, and the struct starts at address 10010014. The first 5 words starting at the address 10010000 belong to the array A, and the next 2 words in memory belong to the struct f. Now let's see how the compiler would generate assembly code for the instructions initializing the array A and the struct f. Here I've rewritten the previous page, removing the declaration of the array and the struct, and compressing the initialization of the struct. So the first 5 lines of the assembly code here correspond with the initialization of the struct f with the denominator field of 20 and the numerator field set to 10. The first instruction loads the address of f into a register. The second instruction initializes a register to the value 20, and then the following instruction stores that value 20 into the location of the denominator field in the struct, which is 4 bytes offset from the beginning of the structure. The next instruction initializes the T1 register to 10, and then store word of that register of 10 out to the 0 offset from F initializes the numerator field to 10. The following instructions shown in blue are the same code from before, that summation of A0 through A3 storing into A4. The first step is to load the address of A into a register, and then load the values of A0 and A1. After that, add those values together, load in the value of A2 into a register, and add that into the T0 that we're keeping the sum of. Load in the value of A3 into a register. Again, remember, A3 is 3 times the element size of the array, which is 4 bytes, offset from the beginning. Add the value that we just read from A3 into the T0 register, and we've got the summation of the 4 elements of the array. Store that value out to the 16-byte offset from the beginning of the array, which corresponds with the 4th index, or rather A4. That's everything today. I hope this has been illuminating.
Okay, so may questions ba for that? So yung next video natin is 13 minutes. So I think medyo sakto tayong 2:30 matatapos. So sorry, medyo nag-extend ata. Mag-extend pala ng konti. So apparently, I think dapat inuna natin yung videos bago basahin yung MIPS files. So medyo may mga umuulit kasi na topics sa videos. Okay, last one. Wala namang questions. So I think then time mag-start.
Welcome. Today's topic is about generating MIPS assembly code from C with function calls. As part of this topic, we will also discuss the call stack, what it is, and how to use it. Procedures are the basic organizational unit of a program and are very important for writing software in high-level languages. The low-level actions that support procedure invocations are listed here. I will use the terms procedure, method, function, subroutine, and subprogram interchangeably. A procedure involves putting the argument's parameters into registers or a stack, transferring control to the procedure, sometimes called calling the procedure, getting storage for the procedure's local variables, performing the procedure's operations, also known as the procedure body, sometimes we'll say executing the procedure body, placing the result of the procedure, its return value, into registers or the stack for the caller to consume, and returning to the place of the procedure call. Two operations support procedure invocations in MIPS. On the call side, there is the JAL, or jump and link instruction. This instruction places the next instruction's address, PC plus 4, into the return address register $RA, and places the procedure's entry point in the $PC. Returning from a procedure uses the JR instruction, which stands for jump register. By specifying $RA as the source operand, the jump register instruction will copy the return address into the program counter. Program execution will then resume at the original PC plus 4 from the jump and link instruction. Note that procedures only have a single entry point, which is where the JAL lands, but may have multiple exit points. This corresponds with writing functions or methods in high-level languages, which start at one location but may return from many points within the function. Also, calling other procedures must be supported. An application binary interface, or ABI, is a set of rules, usually dictated by the processor designer, that specifies how registers should be used by software. These rules must be honored by compilers and by assembly programmers in order for correct, interoperable program behavior. Much of the ABI involves how registers are used. In MIPS, the $A registers are used to store up to 4 word-sized arguments, with $V able to return up to 2 words of return value. The $T registers are temporary, which means they can be written to without any concern but the value stored in a temporary register is not defined after a procedure call because the procedure may have overwritten it. In order to retain data in registers that can survive a procedure call, the compiler or programmer can use the $S registers, which are called callee save registers. A callee is a procedure that gets called, and before it can write into a $S register, it must first save the value in that register and then restore that value before returning to the caller. The procedure saves the value of the register on the program's stack. In this way, we say that the value in the register is preserved across the function call. Two other registers are worth noting now. $SP is the stack pointer, and $RA stores the return address written by jump and link. The memory of a program is laid out in a manner something like depicted here. The instructions are put in the text section, and the variables that are known at compile time, such as global variables, constants, and static local variables, are put in the data section. The rest of the memory is used for data that are generated at runtime, namely the program heap, new and malloc calls, and the stack. In this picture, the stack is shown growing down. Some architectures allow or even mandate that the stack grow up. Most often, we will assume the stack grows down unless otherwise specified. The stack is used by procedures to store local variables, to save registers from obliteration by callees, and sometimes is used to pass arguments and return values. The stack pointer $SP points to the address that is the current end of the stack. When the stack grows down, this is the bottom, as shown in your picture. When a function is entered, often the first thing done by the compiler or programmer is to make room on the stack for local variable storage to store the return address and to save registers. Typically, all of the stack storage required for the procedure body will be reserved at once, rather than adjusting the stack down and up multiple times throughout the procedure's body. Another register, the frame pointer, or $FP, points to the base of the function's frame, which is equal to the value of $SP, the stack pointer, at the time the function was called. Activation record is another name for the procedure frame. When a function returns, the stack is restored to the value previous to the function call, either by adding by the same amount that was subtracted, or by copying the value from the frame pointer. Similarly, the frame pointer of the caller is restored. Up to 4 word-sized arguments can be passed to a function through the $A registers, and a function can return up to 2 word-sized values in the $V registers. Here's an example showing 1 argument and 1 return value passed through registers. Arguments and return values can also be relayed through the stack, which is necessary if more data needs to be communicated across the function call or return than is available space in the registers. In this case, the caller will reserve space on the stack for any arguments or return values that need to use the stack. Here's an example equivalent to the previous, but now showing how to use the stack instead of registers. Using the stack is less efficient than registers. The stack use requires the load word and store word instructions. Store word is used to put data on the stack, and load word is used to get the data out of the stack. It is important to reserve space on the stack by subtracting from the stack pointer before using any store word instructions to store data to it. A procedure that does not make any additional calls is known as a leaf procedure. Here is a relatively simple leaf procedure whose procedure body should look familiar if you watched the earlier video on integer arithmetic. The arguments G through J are allocated to registers $A0 to A3. We will allocate the local variable f to the register $S0 for descriptive purposes. The return value should be in $V0. Here's an equivalent MIPS code generated from the C. Note that the instructions in the assembly that deal with stack manipulation do not really correspond with any instructions in the higher level language. Otherwise, each sub-expression generates approximately one line of assembly code. The leaf function needs to adjust the stack pointer and to save the $S register using store word. Note that I use $S here simply for illustrative purposes, and a more efficient MIPS implementation is possible by eliminating the use of $S0 and simply using $V0 directly. The value of $S0 and of the stack pointer are restored before the function returns. A non-leaf procedure is one that calls another procedure. Non-leaf functions need to preserve the return address before making further function calls. Here is an example equivalent to the previous, but now using two functions instead of one. Here is a MIPS implementation of the two procedures. Note that the non-leaf procedure now adjusts the stack pointer and saves the return address to it by using store word of the $RA register to a stack location. The non-leaf procedure also puts the procedure arguments for the subprogram into the $A0 and $A1 registers before making the call to leaf. The leaf, in this case, is quite simple, since it makes use of the $T0 register, which does not need to be saved before overwriting. Note that the leaf function could be even simpler, since we could put the result of the subtraction directly into the return value register without using $T0 at all. After the return, the non-leaf procedure moves the value returned from the call into a register, and then moves that value into the return value register. This again could be omitted, but is included for illustrative purposes. Note that when I say a value is moved between registers, it's really copying the register. The original value is left in the register that it was moved or copied from. Finally, the non-leaf procedure restores the return address register and stack pointer before returning itself. One final example for today is a recursive implementation of factorial. Here is the C code for a recursive factorial, which returns 1 in the base case that n equals 1, and otherwise returns n times the recursive case, calling fact with n minus 1. Here is a MIPS implementation of the recursive function. This example also shows a reasonable way to write comments that you should adhere to when working on assembly projects in this class. The first three instructions save the return address on the stack and also save the argument to the fact function. The $A registers are caller saved, meaning they are not preserved across a function call. Since fact needs the argument n stored in $A0 after making the recursive function call, we save the argument on the stack. The base case is shown in green. The if expression uses less than for the comparison. There is no branch if less than in MIPS, although there is a pseudo instruction that expands to the two instructions you see here. The SLTI, or set less than immediate, will set to 1 the destination register, $T0, if the source operand, $A0, is less than the immediate, or to 0 otherwise. The BEQ, branch if equal instruction, is used to check if the result of set less than is 0, in other words, not less than, and if so, to take the branch to the L1 target. If the branch is not taken, version has reached the base case. The value of 1 is put in the V0 register, the stack is restored, and the function returns. If the branch was taken to L1, then the recursive case happens. First, the argument is reduced by 1, and the recursive call to fact is made. Upon return, the original value of the argument is restored from the stack, as is the return address, and the stack pointer is restored by addition of 8. The multiplication of the original argument of n by the return value from the recursive call to fact is written to the V0 register, and the fact function returns. Note that I use the mul instruction here as opposed to mult. Mul is a shorthand instruction that does not put its result into the low and high registers, but instead puts the 32-bit low-order result directly into the destination register. That's everything for today. I hope this was illuminating.
Okay, so that's the last video. So afternoon, according to the study guide, is you should now be able to answer a short quiz, which I don't think is uploaded yet. So hintay lang kayo. Or, may long quiz din kayo. So may questions ba before we end? Wala. So since 2:30 na, I thank you for your time. I hope this has been illuminating. If may questions, well, since naka-record yung watch party na to, it will be uploaded to YouTube and is-send ko yung link sa inyo if ever gusto nyong balikan. And if may questions kayo, andyan lang naman yung piazza or you can email. So, again, and have a good day.